Hi everyone, and welcome you all to the computer science session 8 student talk of the 6th Polygon Symposium of Rising Scholars. My name is John, and I am currently a data scientist in the Chicago area. Previously, I've been to Connecticut, like we spoke about, and right now, and then I went to school in Michigan. And I'll be moderating the talk today. So the goal of the symposium here is to celebrate and showcase the hard work of our college's scholars, most of them who are middle to high school, and all of them who have tirelessly worked on their projects over the past couple of months. So today we have 3 presenters presenting on a variety of topics, really exciting ones, and a fellow Apologist member of ours will be scoring each student's presentation, and this will help us determine the prize for the winners after the event. Please type your questions in the chat if you have any questions for the speakers, and we will give 2 minutes for questions after each of the presentations. So for today's speaker would be Aditya Machiroutu and Joshua Chen and William Gao. So yeah, and I think whenever Aditya, I think if you want to go first and you're ready, feel free to take it away.
All right, hopefully you guys can see my screen. Let's get started. Hello, my name is Aditya, and I'm a junior in high school. For my project, I conducted research on an exciting new field of artificial intelligence and machine learning, data poisoning. So first, let's start with an overview of what machine learning actually is. Machine learning is a branch of artificial intelligence, which is the development of systems that can perform tasks that usually require human input. In machine learning, systems, or the computer, learn through data input given by humans in datasets. A system applies pattern recognition through complicated processes like neural networks and natural language processing to train on the dataset given. Once a model has trained, it can make decisions without human input. This is an example of an image classifier machine learning model. So when training your model, it will show you a picture of cats because your training data is filled with cats. That way, when the model runs on a real data set of cats, it'll be able to predict a cat. If you're given a picture of a dog, for example, it wouldn't be able to predict what it was. Data poisoning is an adversarial attack that targets a machine learning model. Its goal can either be to ruin the model or gain specific results. When successful, it can bypass systems and gain access to important machine learning models. In this example of the machine learning pipeline, the training data given has some poisoned data. As a result, although you train with images of a cat, the model will lead you to predict a dog. When applied to real data, any picture of a cat will predict of a dog. Although this doesn't sound too dangerous, real-world examples like a stoplight detector for self-driving cars detecting a red versus a green light can be dangerous when it's poisoned. So how do you actually poison your data? So there have been many different methods created on how to poison a machine learning model. In all attacks, you have clean images, which are called base images, and they're modified by an attacker that belongs to a certain class, which an attacker either wants to change or destroy. For example, if you have a picture of a dog in the dog class of an animal classification model, a working poison could classify this dog as a turtle or any animal of their choosing. The first question is whether an attack is triggerless or backdoor. Backdoor attacks alter their target during inference, a step in the training, by adding a trigger. These triggers can be a small patch to an image that are so small they aren't recognizable to humans. Because machine learning models learn through pattern recognition, small pixel changes can have devastating impacts on model accuracy. A clean label backdoor attack occurs when there is an adversarial change to each base image. A patch is added to each image to regenerate a final image. A hidden trigger backdoor attack is slightly different. Poisons are crafted to remain more close to the base image, so it's less likely to be noticed, but they collide in feature space with the patched image from the target class. Triggerless attacks, on the other hand, cause the victim to misclassify an individual image called the target image without the use of a specific patch. There are many different triggerless attacks as they've rose in popularity over the past couple years, but the most prominent are feature collisions, convex polytope, and bullseye polytope. Feature collisions are when poisons are crafted by adding changes in base images so the model sees them as a target. So instead of adding like an actual patch, you're changing the image itself. Convex polytope works by choosing a target image. Selected poison images are designed to surround the targeted image in a polytope in feature space, which I'll talk about in a little bit. It's a slightly more optimized version of feature collisions. And then there's bullseye polytope, which is a slightly more improved convex polytope, which focuses on the actual shaping of the convex polytope. However, it has many limitations in practical usage. So as mentioned earlier, convex polytope was created as a more optimized way of poisoning using feature collisions. So feature collisions work by adding small changes to the base images so their features look like a target. But this can be really difficult to implement in a black box setting when you don't know anything about your victim's data set and its model architecture, because it's really hard to make your poisons look like a target when you don't know how the target looks. As a result, even when the poisons collide with the target, they won't collide with the unknown target model due to data restrictions and generalization errors, and this means that the attack will most likely fail. Instead, there needs to be a looser constraint on the poisons so that the attacks have a higher chance of working. Professor Steinhardt, one of the pioneers of data poisoning, found that a set of poisons from the same class is guaranteed to change your class label into whatever you want to poison it if that target's feature vector lies in the convex polytope of the poison's feature vectors. And this condition is a lot easier to achieve as it allows way more leeway, and poisons can lie much farther away from a target while it alters on a much larger region of feature space. Using optimization equations and procedures, a set of poisons forming this polytope can be created to attack poisons. Okay, so this graphic here shows exactly what feature space exactly is. So when a machine learning model runs through its data, it naturally aligns like images with each other relative to their many parameters. For example, if a machine learning model detected whether an image was a cat or a dog, there'd be a section of feature space dedicated to cats and one for dog. These images are aligned based on their features, which are the number of parameters that a system takes into account when classifying an image. So like the number of legs something has or the number of ears something's had. From this model, you can visualize how feature collision attacks attempt to get close to a targeted image, as shown on the left, while convex polytope attacks attempt to surround the target more. I chose to focus my research on and testing on convex polytope. This is because it's currently the most prominent poisoning technique used and has had the best success rate when it was benchmarked. So these were the major results that I gathered in my research. So the accuracy refers to the percentage of images that were classified correctly. So a lower accuracy means your poison was more effective. So with no poisons, the data set ran with a model accuracy of 94% and took around an hour, 9 minutes, and 12 seconds to train the 60,000 images in my data set. Default convex polytope, which is the standard usage, has 250 poisons and a model accuracy of 25.12%, and doesn't add any like additional time to train and test the data set, which is really good. So I tried expanding the polytope radius by a factor of 2. So the poisons are less effective in this case, which makes sense, but they had a lot more variance. The major problem is that the time it took to run the model doubles, which is a major issue, especially when data set sizes become bigger, way past like 60,000. By trying to focus on changing the polytope to be more centered like bullseye polytope, I didn't have too much success, with my poisons resulting in the model having a 74% success rate, but it still had a regular amount of time that it took. The last variable I changed was the number of poisons. I found this to give me the most clear results in my data. As shown from the data above, using less poisons dramatically decreases the poison strength, but it also decreases the time for completion. Using more poisons increases the poison strength, but the time for completion increases by a larger factor. I found the most optimized number of poisons to be around 300 for every 60,000 images, which is 0.5% of the data set. Okay, so to continue working with the field of data poisoning, I'm interested in creating my own poison from scratch rather than just changing how convex polytope works and optimizing it. I'm also currently developing a research paper of my results where I break everything I've talked about today from a more technical perspective and it's more detailed. I'm also interested in connecting with professors with more extensive research in data poisoning. I can connect to them so I can use my research and connect even more. Thank you for listening.
All right. Thanks, Aditya. That's a really interesting presentation. Great work on that. All right, and then we have our 2-minute question session. Right now, I'll open the floor to any questions. You can either type it in the chat or in the Q&A.
Okay, I have a question in the chat. How does one actually poison a data set? Your red light example, for instance. So this could be the two biggest ways is either you have access to a data set before a model can run on it, or you have access to model architecture and you're using the model architecture, and then from there you can bypass systems to actually poison your data set. Okay, I have another question. How does one actually defend against that poisoning? So when I first started this project, like around July and August, I actually wanted to come up with ways of almost curing data poisoning because it's one of the largest threats. And as of now, there's no real solution to it because if you're able to poison a data set, there's nothing you can really do as the model is compromised. However, there are currently things like in the works on how to actually defend against it. But as of now, currently published, there is no actual real working defense against data poisoning. As for plans to extend my research, yes, I do. I want to continue working with this project in the future. I'm currently developing a research paper where I walk through all of the things I talked about today, and I'm also in contact with professors like Professor Steinhardt, where I can work with them in the future, because although they did a lot of their data poisoning work in like 2017, 2018, it's now 2022 and they're still publishing stuff. They're still coming up with new ideas. I talked about some of the poisoning techniques like clean label, hidden trigger, convex polytope, bullseye polytope. There's always more that are coming out. Yeah. Okay, I have another comment. So I was shocked by the relatively small percentage of poison that was needed to affect the model. Is it realistic to poison from the real world? So yeah, it's actually fascinating. The way data poisoning, how effective it can be, especially because when you're talking about convex polytope, it's every single piece of convex polytope is run by optimization equations. So because of that, you don't need a lot of poison in order to poison like really, really large data sets. Like 60,000 images is actually relatively small, especially when you're comparing to like Google's data sets, or like, let's say you have a data set of all of Google's images, stuff like that. It doesn't take a lot of data. 0.5% was what I found to be the most optimized, but the only two variables that I really considered was the time it takes to run the model, which is super which matters a lot, but also the poison percentage. But if your time that it takes to run the model is not something that you care about, there is a lot you can do with just a small number of poisons.
All right. Yeah. So if that's all the questions for now. We will invite our next presenter, Joshua Chen.
Okay. Yeah, I think I'm sharing my screen correctly. So I'm Josh, and my project is a web application called Text to Video that simplifies the process of creating video presentations by converting text into narrated slideshow video. And my mentor is Jared. So during the recent increase in distance, oops. Wait, I don't think I'm sharing my screen correctly. Let me check.
You had it correct right before you stopped sharing.
Oh, I did? Okay. Like that?
You have moved your window out of the way.
Oh, okay.
You get that presenter view out of the way.
Okay, yeah. Okay, like that?
Perfect.
Okay, yeah, I'll just close this. Yeah, I don't know how to hide it, so I'll just close it. Okay, yeah. During the recent increase in distance learning and remote working, teachers, students, businesses, and others are relying on video presentations more than ever before. But learning video editing software and creating videos can be time-consuming, effort-intensive, and you have to require technical know-how. But text-to-video fixes all these issues. So text-to-video is a web application with an easy-to-use, user-friendly interface that lets people without any video editing experience create narrated presentations quickly and easily. And to make text-to-video, I used technologies like Flask for building the interface to upload the audio and script to the website. A program called Gentle, which basically it gets timestamps of when each word in the audio was said. And this type of program is called a forced aligner. FFmpeg for connecting the images and audio together to form a video. Docker for containerizing the Gentle server and text to video together. And DigitalOcean for deploying the app to the web. So this is how it works. So first, users just upload a script. They write a script for their narration for their video. So in this example, the script of the video is Romeo and Juliet is a play written by William Shakespeare. It is set in Italy and is about the love between two young people from noble families that are enemies. It has been adapted to opera, ballet, television productions, and movies. So after the user has written the script, they have to place image descriptions in brackets where they want them to appear. So in this example here, a picture of a Romeo and Juliet painting will appear as the start of the video. Then after the narration says, Romeo and Juliet is a play written by, a picture of William Shakespeare will appear. And at the same time, the narration will say William Shakespeare. And the next picture that will appear is a picture of Italy, and so on. So yeah, basically just place your images you want to appear in brackets. So once you create the script, you upload it to the website, and you either choose to use a computer-generated voiceover or use your own audio file. And if you choose use your own audio file, you record your own voice and upload it onto the website, and text to video will align this audio file to the images for you. Or you can use a computer-generated voiceover, which in that case, text to video uses text to speech to generate your audio for you. And you can either choose to upload your own images or just use the default image search feature. And if you don't click this check mark here, the upload your own images check mark, then text to video will look on Google for images of your image descriptions and select one of the top 5 images randomly on Google and use that for your video. Or you can either, if you select the upload your own images option, text to video will prompt you to upload images for each image description you want. It will align it for you. So after you select all these options, just click create video, and then text to video will have your final presentation. So here's a demo of how it works. So yeah, so this is the website. So, and in this demo, I'll pause it. In this demo, I'm using the same script that I showed you before about William Shakespeare. So yeah, so I upload the script that I wrote. That was the one I just showed you. And I upload an audio file of me reading the script. And I click create video, and then soon the video will appear. So I play in the video.
Romeo and Juliet is a play written by William Shakespeare. It is set in Italy and is about the love between 2 young people from noble families that are enemies. It has been adapted to opera, ballet, television productions, and movies.
Yeah, so just chat. Okay, so just from the script and the audio, a text to video generates this whole video for you, which is pretty cool. Okay, so this is how the code works. So first, users upload an audio narration and a script to text to video. Then text to video searches for Google on Google for the images and downloads them. And then it uploads the audio and script to the Gentle server. And Gentle returns timestamps of when each word in the script was said. And text to video writes these timestamps to a text file. And it sends the audio and images and this text file that it wrote of the timestamps to FFmpeg, which then uses the text file of the timestamps to combine the audio and images together to create a final video. And it sends this video to text to video, who then displays it to the user. Okay, so I'm running an experiment to compare text to video to PowerPoint. So in the experiment, 5 participants create a video presentation 2.01 times faster on average with text to video than PowerPoint. And all participants thought text to video's quality was equal to or higher than PowerPoint. And all participants said they preferred text to video or had no preference. And to determine if these results were significant or not, like determine if these results just happened by chance or if they really meant something, I performed a paired t-test to compare the video quality time, the video creation time, and the quality of text to video in PowerPoint. So the results were that there's statistically significant evidence that people created videos quicker with text to video than PowerPoint. And the p-value was 0.007, which means that if the people create videos in equal time with text to video and PowerPoint, then there's only a 0.007 probability that we would get the results that we did, or a bit more extreme. And because our p-value is so low, because the probability of this happening is so low, which was less than our alpha value of 0.05, we have convincing evidence that people create videos quicker with text to video. And I performed another paired t-test to compare the quality of the video between text to video and PowerPoint, but the results weren't statistically significant, which means that it could have happened by chance. For further development, one feature I want to add is the ability to add subtitles to your video. This would make it more accessible for people with hearing impairments. Add the ability to record your own voice on the app, so you don't have to go to another website to record your voice, then download it from that website and upload it on the app. And one feature I want to add is, instead of choosing a random image from Google, let users choose which image to use from Google. It's displays the top 5 images from Google, and the user gets to choose which image to use for the video. And yeah, that's text to video. So are there any questions? What real world applications? Yeah, so a teacher wants to present something to their class. They don't really know how to use video editing software, since I'm sure a lot of teachers don't know how to do that. For asynchronous learning or something, they have to record a video for a PowerPoint or something, then use this app to just create it really easily. And it takes really short amount of time. They don't have to learn an editing software like iMovie or something to create the video. They just can use this app to do it quickly. Basically, anyone who wants to create a PowerPoint with narration can use this app. Yeah. Someone's personal photo library. Oh yeah, there actually is a feature where you can upload your own images. So instead of searching for images on Google, you upload your own images and uses those images to sync with uh, audio and script. And actually, it's on the web. If you go to like writemyvideo.com, it's on that website, and you like play around with it if you want. Yeah. Okay, well, those are all the questions. Then I guess I'm done, unless someone else has any more questions.
All right. Thanks, Josh. That's a very interesting presentation. All right, our next presenter would be William Gao.
All right, I'm gonna. Wait, I'm gonna have to. All right, so what I did was understanding lyrical content and song popularity using interpretable machine learning. And my abstract is that the purpose of this project is to predict song popularity, grouping songs, and find correlation among lyrics. Music's X matches million song dataset was used for lyrics and artist data. Google's YouTube API combined with a YouTube web scraper was used to find popularity for the songs. The results showed that lyrics and song popularity are correlated with an R squared of 0.092. And so it's feasible to predict song popularity by lyrics. Before a song releases, it can be hard to tell whether it'll take off, and the ability to predict a song's popularity based solely on lyrics is important to illuminate the success of a song before it's released. Existing works have come across two major problems. They've used curated data sets based on a complex knowledge of music, and they've discredited the hold lyrics have on the popularity of music. Curated data sets are impractical for real-world use, as it takes special skills to be able to make a curated data set. Here, the lyrics are very simply sorted so that the data set could be expanded easily by anybody, and using these simply sorted lyrics, we're able to predict the popularity of a song. Data collection. 5,858 songs with their lyrics, artists, and popularity were analyzed. Lyric and artist data was found using the Music's X Match million song dataset available online. It contains lyrics in a bag of words format. Each song has a list containing all of its words and how many of those words there are. This list omits obscure words that make it outside of the 5,000 most common words that Music's X Match has chosen. Popularity data was found using Google's YouTube API. The YouTube search list function was used to search for the song's name and the artist name, followed by the word song. The YouTube ID of the first 3 videos found was put into a YouTube web scraper to find the number of views that YouTube video had and the view counts of the three videos, the higher count was used as the popularity data. Taking the highest, so the reason that I did this was because using YouTube as a popularity metric, sometimes like more recent videos would be recommended instead of the video that had the most views. So I took the top 3, and usually like the video with the most views was in the top 3. All analysis was run in Spider using Python, and data storage was handled using Panda's Python data analysis library. And machine learning was achieved using scikit-learn. The method can be split into 3 parts: predicting song popularity based on lyrics using interpretable machine learning, grouping songs using linear and non-linear dimensionality reduction, and predicting missing lyrics using interpretable machine learning. Here are the 2 runs of random forest regressor. The x-axis is the predicted values, and the y-axis are the real values. Random forest is a meta estimator. It splits the data set into multiple parts or subsamples, and then it fits a decision tree to each subset. The estimator then averages to the predictions of the subsets. And the task of predicting popularity solely based on lyrics is extremely difficult. And it's compounded by the fact that lyric order and timing isn't accounted for in my data set. And popularity is also at the whim of a lot of other factors, such as how popular the artist is, how popular the genre is, and the actual like tune of the song. So whether or not a song becomes popular is at the whim of a lot of factors that I can't really control. And so I only have lyrics, which means that my expected correlation would be low, but the fact that I found any correlation at all is considered a success. And the random forest regressor was able to find correlation between lyrics and song popularity. And this is Bayesian ridge, which is a very different type of machine learning. And again, the x-axis are the predicted values and the y-axis are the real values. Bayesian ridge regression is a variant of ridge regression, which is undertaken in the context of Bayesian inference. Ridge regression estimates the coefficients of multiple regression sets in sets of linearly independent variables are highly correlated. So Bayesian ridge regression was given the same task as random forest regressor, and it was able to produce slightly stronger results, but it tended to group the songs in like a tighter bunch at the start. And it's also still held back by the limitations that I discussed earlier about how I don't have many variables to train on. I only have the lyrics and basically just what words are in the song. And this is my SHAP analysis. And SHAP is a reliable way to interpret how significant factors are to a model. So SHAP changes the inputs of a model and observes how the output differs. Here you can see the top 20 most impactful words according to the SHAP. How far left or right it is on the graph signifies the word's impact on the model output, and the color signifies its feature impact. So a word like love, you can see up here, has high feature value and high positive SHAP value. So it's a word that would highly positively influence the predicted popularity number. And a word down here like deaf has high feature value, but a very negative SHAP value. So it would highly negatively impact the popularity of a song. I have other results, but I don't really have time to talk about them. And so the conclusion is that using interpretable machine learning it's possible to predict the popularity of a song based on the lyrics alone. And the ability to predict the popularity of a song based purely on lyrics has great commercial value due to its ease to set up and the valuable information it can give. So something that's more complicated, say something that where I have to punch in the timestamps for when the word goes out or put the tune in, would be very hard to set up for the average person. While here, you can literally just take your lyrics and put it in, and you can just, that's it. And so in the future, an app can be developed utilizing this research, and the app will be an invaluable tool for both smaller and bigger musical artists. So do you have any questions? Well, personally, I wasn't.
Hey, Ren, can you repeat the question?
What was the most surprising thing you learned during your research? And so the most surprising thing, I think, is that the machine learning was actually capable of finding correlation because of there were so many factors that I said earlier, like how popular the artist is determines like how much popularity a song has. The fact that I used a bag of words format, basically all the AI could know is how many words of like how many times does the song say I or love, and it was still able to predict popularity based on that. So I was pretty impressed by that. Yes, actually. So something that's really interesting that happened is
What was
that
that question, Ryan?
are there any biases in the data that you should consider? And so if you notice, a lot of Spanish words actually got a lot of like the AI, the machine learning thought that the Spanish words increased song popularity. And I think that this is because the data set I used only included Spanish songs that are very popular because it was a mostly English data set. So any songs that were like Spanish songs, they had to be very popular to make it into that English data set. So that's why a lot of Spanish words have high significance, basically. And also I determined popularity using YouTube. So there could be, for instance, some songs that just aren't popular on YouTube for some reason. Where? Oh, this is just it's just a visual glitch. It's just like I like something, but there's a percent in front of it because it's the most common word and the data set just put a percent there. I'm not quite sure why.
All right. Any other questions? Okay. Great. Thanks, Will. Yeah, again, really exciting presentation there. Okay, so yeah, right now we've gone through all of our presentations for this session. Yeah, and thank you for joining.
Thanks, everyone.